All right. This is cs50, Harvard University's introduction to the intellectual enterprises of computer science and the art of programming. My name is David Malin, and I actually took this class myself some years ago, but I almost didn't. It was my first year in college, and my roommates and I were living in Matthews Hall, for those familiar. Nice, Matthews. Our claim to fame, actually, at the time, was that our room was literally Matt Damon's just 3 years prior. So onward from that. But my first year, I didn't really have the nerves to set foot in this classroom, let alone computer science. In fact, for me, computer science, and CS50 in particular, was very much this class to beware. I was kind of comfortable with computers, but I certainly wasn't among those more comfortable with computers, and so I shied away my first year. Instead, I actually took a whole lot of classes in government. In fact, in high school, I was really enjoying history. I loved this constitutional law class that I took my senior year of high school, and so I figured, okay, if that's what I liked in high school, and if that's where my comfort zone was, that's probably what I should be doing in college. And so I essentially declared as my concentration or major government for the first year and a half of school. But my sophomore year, when I was living actually in Mather House instead, okay, no one from Mather. In Mather House instead, I sort of followed some friends, I think, the first week of class in September of that year to a class called CS50. And honestly, once I stepped foot in that classroom, the professor at the time was a famous computer scientist by the name of Brian Kernahan, now at Princeton. I was hooked, and literally would I go back thereafter on Friday evenings when at the time problem sets were released and sit down at 7, 8 p.m. on Friday nights and dive into homework, which isn't necessarily something we recommend per se, but for me it was this sign that wow, I've sort of found my calling. I found my classmates here on campus. And that's not going to be the case for everyone. Certainly we have no expectations that after taking one computer science class that you will or might want to take others, but what's so empowering about computer science, and CS50 in particular, is it's so applicable to the broader world, whether you're in the arts, humanities, social sciences, natural sciences, or beyond. It's just so applicable, the concepts and the practical programming skills with which you will exit a class like this. Now, it's going to be challenging along the way, and indeed, I put in my time back in the day, and even I did find it challenging. And here, for instance, is a photograph of a very famous MIT hack, so to speak, from down the road, whereby it communicates that getting an education from MIT is like trying to drink from a fire hose, which is to say there's going to be so much information, so much new stuff, that certainly on any given day of the week, you're not going to be able to absorb all of it that first time around. But at the end of the day, it's through that challenge, putting the time in, that the returns are therefore just so much higher at the end of the course. And indeed, will you walk out of the course with a much better understanding not only of computer science and programming, but ultimately how to teach yourself new technologies and beyond. For the next 3+ months, we have teaching fellows, teaching assistants, course assistants, and myself by your side, sort of guiding you through the course's material. But the goal by term's end is to take those and leave those training wheels off so that you're well equipped to sort of go teach yourself new ideas beyond the class itself. Take comfort, though, in knowing that most CS50 students have never taken a CS course before. And indeed, as per the syllabus, what ultimately matters in this course is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. And when you began is thus today. And so consider just how comfortable or uncomfortable you are with computing, let alone computer science and programming, particularly if you've never explored either in a classroom before. And consider the delta just a few months from now that will really describe how far you have come. And that is all that matters, not how much the student to the left, to the right, in front, or behind you right now knows. With that said, let me add some additional inspiration, if I may. Here's a photograph of my own very first homework assignment in CS50 from 1996. And I will draw your attention to the fact that even though this is a so-called Hello World program that we'll play with ourselves next week, it is pretty much literally the shortest, easiest program you can write in a programming language called C. I still somehow got -2 on my very first homework assignment, which is to say, we're all going to make mistakes along the way, but the goal will be to learn and enjoy that process here on out. At the end of the day, too, like me, you'll exit with your own proudly held I Took CS50 t-shirt, as is our tradition, too. With that said, there's so many other traditions within CS50, both on campus and off. And in particular, do we try in CS50 to provide not only the academic support structure that you might want going through the class, but also a collective shared community experience, which is to say in just a few days, we'll start off the term formally with CS50 Puzzle Day, which is not only an opportunity to get together with friends with pizza and prizes and also logic puzzles of sorts, but really to send the message that computer science itself is not about programming, it's not about C, it's not about Python, it's not about programming languages per se, but about problem solving, ever more so collaboratively with other smart people by your side in this class or beyond. And indeed, are there, toward the end of the semester, reinforcements of the same by way of a little something that we call the CS50 Hackathon, which will be an opportunity overnight to dive into your own final projects, the capstone of this course, thereafter followed by the CS50 Fair, which will be a campus-wide exhibition for students, faculty, and staff across campus of your very own final projects, be it your very own web app or mobile app or anything else you decide to create by term's end. And indeed, the sort of objective at the end of the day, truly with that final project in particular, is going to be to create for yourselves, for your classmates, for attendees, something that we didn't even teach you how to do. And indeed, that will signal ultimately that you're indeed on your way and ready. Toward that end, thought we would give you a sense of CS50's past by way of this short video, if we could dim the lights, that paints a picture of all that awaits here and beyond. So welcome aboard to CS50 and computer science itself. So what is computer science? Well, put simply, it's the study of information. Like, how do you represent it and how do you process it? But more fundamentally, what we'll teach in this class is computational thinking. That is to say, the application of ideas from computer science to problems of interest to us within the class and problems of interest to you after the class. And so at the end of the day, what computer science really is about problem solving, ergo that sort of global applicability. And by problem solving, we mean something quite simple. In fact, we can distill it as follows with this mental image. This is problem solving. You've got some problem to solve, thus known as the input that you want to solve. And the goal, of course, to problem solving is to actually produce a solution. So the output in this model would be the solution. The interesting part ultimately is going to be in how you process that input and turn it into that output, ergo solving problems. But before we can do that, we all kind of have to agree how to represent these inputs and outputs, especially if we want to do it in a standardized global way using literally computers, be them laptops, desktops, phones, or most any other kind of electronic device nowadays. So how can we do that? Well, there's different ways to represent information in the world. For instance, if I were to take attendance old school style, maybe in a smaller room, I might do 1, 2, 3, 4, 5, 6, 7, and so forth, and just count people on my human hands. That's actually known as unary notation, otherwise mathematically known as base 1, because you're using your fingers literally in this model as digits. But a little quick question, how high can you count with one human hand? 5 is incorrect if you use a different base system than 1. So it's obviously correct if you're just using unary and just counting 1, 2, 3, 4, 5. But I dare say I can come up with more patterns in my human hand alone that would enable me, without a second hand or a couple of feet, to count higher than 5. In fact, maybe for those more comfortable, how high could you actually count on a single human hand, perhaps? So 31, believe it or not, is in fact the correct answer. But why? Well, here I initially started pretty naively, 1, 2, 3, 4, 5, and I just kind of combined all of my fingers and counted the collective total. But what if I'm a little more clever and take into account the pattern of fingers that go up? So maybe this is still 0, this is 1, But now maybe we just agree universally that this is 2, even though it's just my single pointer finger. Maybe we all just agree that this is 3 with 2 fingers up. Maybe we agree that this is often offensive with just 1 middle finger up. But this would then be 4. This could then be 5. This could then be 6. This could be 7. And if I keep permuting my fingers in this way, allow me to spoil it, this would be, in fact, 31. But again, why? But the difference here is that we're no longer using unary, or base 1, as a mathematician would say, but rather base 2. Because if we take into account not just the total number of fingers that I'm using, but whether each finger is down or up, being therefore in 2 potential states, down, up, A, B, black, white, however you want to distinguish those 2 states of the world, you're now operating what's called base 2. And perhaps more familiarly, even if you're not a computer person per se, this is the so-called binary system. And odds are, even if you're not a computer science person at all, you probably generally know that computers only understand or speak what alphabet, so to speak. So 1s and 0s, 0s and 1s, otherwise known as the binary system. And in fact, there's a term of art here that's worth noting. When you're using 0s and 1s, which of course are a total of 2 digits, you have binary digits, so to speak, bi implying 2, which means there's 2 possibilities, 0 or 1. If we actually get rid of some of these letters and then join these 2 phrases, here you have a technical term that is a bit. A bit is just a binary digit, which is to say it's a 0 or 1. And this is in contrast, of course, with the system you and I know as the decimal system, dec implying 10, because in the real world, you and I daily use 0 through 9, which is 10 possibilities. Computers only use 0 and 1. That is to say 2 bits to represent information instead. So how do we represent this information, especially when at the end of the day what we're using are indeed computers and electronic devices? Well, if I want to represent 0, I can actually think of this as kind of analogous to the physical world. Maybe I have a light bulb that's off or on, controlled by a switch that turns it off or on. So you can think of a binary digit that is a 0 as really just being a light bulb that is off. By contrast, if you think of a 1 in the digital world, as of course being the second of 2 possibilities, you can think of that in the human or analog world, the physical world, as being a light bulb that is on. And in fact, what's inside of your Mac, your PC, your Android phone, your iPhone are millions of tiny little light switches known as transistors that just can be turned on or off, and essentially you can use those transistors to store information, because if you want to store a 0, you turn one of those switches off. If you want to store a 1, you turn one of those switches on. Of course, that sort of invites the question, well, how do we count higher than 0 or 1? Well, we would seem to need to use more than just maybe a single bit, a single light bulb. So if we wanted to count higher than, for instance, 0 or 1, why don't we go ahead and maybe do this? So just so I have some place to put these, let me borrow some of our actual physical light bulbs here from the stage. And let me propose that now, with 3 bits on the stage, 3 light switches, 3 transistors, whatever metaphor you're most comfortable with, this is how a computer would represent a 0, because all of them are off. So it's off, off, off. But if a computer wanted to count to 1, we could do naively this. We could turn this on. And if a computer wanted to represent 2, we could do this. And if a computer wanted to represent 3, we could do this. But I'm kind of painting myself into a corner and not using these light bulbs as cleverly as I could, because at the moment I've only counted as high as 3. So if I want to count to 4, to 5, to 6, I'm going to need more and more light bulbs. Can we be a little more clever? Well, again, someone else who's among those more comfortable, what's the spoiler here? How high, using binary 0s and 1s, could I count with 3 light bulbs total? And back? Yeah. So 7 here is the answer. And if that too, you're sort of wondering, how are people figuring out 31 and 7? That's the goal at hand here. So let me do this. Let me turn all of these off again so that my 3 light bulbs or switches, again, represent 0. And the first one's easy. This is how a computer would represent the number 1. It would be on, off, off. How, though, is a computer going to represent 2? Well, just like my proposed finger example, let's do this. Let's turn this one off and this one on. That is how a computer would represent 2, by saying off, on, off. In other words, 0, 1, 0 would be the way to pronounce it digitally. What if I instead want to represent 3? That's how on my finger I did this with 2 fingers. Well, I'm going to turn this one on. This is 3. Now this will, for those less comfortable, be non-obvious. This now is how I would represent the number 4. This is how I would represent 5. This is how I would represent 6. And this, as per the spoiler, is how I would represent 7. So perhaps very non-obvious what it was I just did or why I chose those patterns. But I dare say if you sort of rewind in your mind's eye, or literally later on video, you'll find that I actually did show you 8 distinct patterns of light bulbs. The first one was off, off, off. The last one was on, on. And there were another 6 total in between then. Well, wait, why 7? Well, if you start counting at 0, and I claim there's 8 possibilities, you can only count from 0 to 7, as we will soon see. So how are these patterns coming about, and what is it that our computers are actually doing? Well, it's actually doing something a little like this, quite like in decimal. So in the human world, you and I are very much in the habit of using base 10, 0 through 9, aka decimal. Well, how do we use it instinctively as humans? Well, what's this number obviously on the screen? 123. But why is it 123? Like for years, you haven't really thought about why this pattern of symbols or digits on the screen, 1, 2, 3, represents mathematically this number that you know obviously as 123. But if you rewind to grade school, odds are, like me, you were taught that the rightmost digit is in the ones column. This second digit is in the tens column. This digit is in the hundreds column, and so forth. So even though none of us have to do this math explicitly, what you're instantly doing is 100 times 1 plus 10 times 2 plus 1 times 3, which gives you 100 plus 20 plus 3. Oh, that's why it is 123, because these digits in this order have that significance. The digits to the left have more weight, so to speak, than the digits to the right. So what can we take away from this? Well, let's generalize it first as just any 3-digit number. So number, 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 the ones column, the tens column, the hundreds column. But there's some math going on there, and it's not particularly sophisticated. Those are actually powers of 10. So 10 to the 0, 10 to the 1, 10 to the 2. And there's your decimal system. Because the base in this value is a 10, that's because there's 10 possibilities for each of those placeholders, 0 through 9. But in the binary world, in the world of computers, where all they have are zeros and ones, why? Because all they have physically is transistors, tiny, tiny, tiny light bulbs that can be off or on. If you only have 2 digits to play with, the 10 base should, of course, become a 2 base. And now if we do some math here, 2 to the 0, 2 to the 1, and 2 to the 2, you get the ones column, the twos column, the fours column. And if we keep going, 8, 16, 32, 64, 128, and so forth, it's powers of 2 instead of powers of 10. But this is to say computers represent information in exactly the same way you and I have since childhood, but they have fewer digits at their disposal. So these columns need to be weighted differently. So we can still count from 0 all the way up toward infinity. So what does this mean? Well, here we have 3 bits on the screen, 0, 0, 0. If we were to convert this now mentally or on paper pencil to decimal, how do we do it? Well, 4 times 0 plus 2 times 0 plus 1 times 0, that gives us the mathematical number you and I know as 0. That was 3 light bulbs, off, off, off. Well, what if we turn on 1 light bulb all the way on the right? What decimal number does this binary number, 0, 0, 1, represent? Just 1, because it's 4 times 0, 2 times 0, 1 times 1. Here's where things got more interesting, even if non-obvious in light bulb form or even physical hand form. 0, 1, 0 in binary is what in decimal? 2, because it's 2 times 1, and that's it. 0, 1, 1 in binary is, of course, now 3. This is now 4. This is now 5. This is now 6. And 7 on, or 1, 1, 1 is the highest we can count with these 3 bits. All right, so how might a computer intuitively count as high as 8? What do you need to do, presumably? You're going to need to add a bit. So you need another light bulb, another switch. You need more memory, so to speak, to use nomenclature with which you're probably familiar. So in fact, if we change all of those to 0, but we give ourselves 1 more bit for a total of 4, that's got to be the 8's place, because it's just another power of 2. So 1, 0, 0, 0 is the decimal number 8. You don't say 1,000 in binary. You literally say 1000, but that is the number you and I know as 8. And you can keep going up and up and up. And how then computers with Excel or any kind of number crunching software count really high and keep track of really big numbers? The computer just throws more and more transistors at it, more and more bits to count higher and higher and higher than this. Turns out, though, 1 bit, 3 bits, even 4 bits aren't that useful in practice because, like, literally you can count as high as 7 or maybe 15 or 31. So more commonly, as is commonly known, is to use a byte of bits instead. How many bits is in a byte for those familiar? So it's just 8. Why 8? It's just more useful than 1 or 2 or 3 or some other number. And as an aside, it happens to be a power of 2, which is just useful electronically as well. So a byte then is just 8 bits. And here are those columns I rattled off the top of my head. Here is how a computer would represent 0 in decimal, but using 8 binary digits or bits. Little trivia, and again, this is not what computer science is about, but it helps to sort of know sort of the lower bounds and the upper bounds of these kinds of values. How high can you count with 8 bits or 1 byte? If this is 0? Yeah, so it's actually 255. So if I were to change all of these zeros to ones and then do some quick mental or calculator math, 128 plus 64 plus 32, 16, 8, 4, 2, and 1 would actually give me 255 total, plus 0, which gives me 256 total possibilities. So this is only to say, this is not, again, the kind of math we'll frequently do, but you'll commonly see in the computer world and programming world powers of 2, numbers like 255, 256y, because these are the common units of measures that systems tend to use. So let me pause here and see, with respect to binary, zeros, ones, transistors, and the like, any questions or confusion we can clear up? A really good question. Why are bits just on or off instead of maybe sort of 0%, 50%, 100% by playing with voltages? So the voltage inference of yours is actually correct. That's what computers typically do. Maybe they use 0-ish volts to represent 0, maybe 5-ish volts to represent 1. It turns out it's just really easy to do extremes in computers. If you start to split that range of voltage levels for those who remember any of their electricity, it just gets harder and harder to be exact. And if you get things a little too murky, you might mistake a 0 for a 1 or a 2 or a 3. So it turns out it's just simpler to use the binary system. But there do exist computers known as ternary computers that actually use 3 values, 0, 1, and 2, which is somewhere, of course, between binary and decimal. But you can do different things. It's just simple on and off. And case in point, I don't want to really be dramatic and turn off my computer, but if I pulled out the power plug, that could be off, literally, aka 0. Plug it back in, that's a 1. There's just a cleanliness and simplicity to that. Other questions or confusion that we can clear up? No? OK, so if you're in agreement for the moment that, OK, using just zeros and ones, we can represent any number we want from 0 on up, let me propose that we do more useful things with our computers and our pockets and desktops and laps, like represent letters for the sake of Google Docs, Microsoft Word, or any kind of text that we might want to write. So knowing now that computers only use zeros and ones, and therefore only contain hardware like transistors, how could you represent something like a capital letter A in English inside of a computer, which of course is not a number anymore? Like, what could we do? Yeah. OK, yeah, so we could take the alphabet A through Z in English, and we could just assign each letter a number. And honestly, that is not only the correct answer, it's really the only answer. Because at the end of the day, if all you have are zeros and ones available to you, that is the entirety of the potential solution to this problem. So it turns out that, yes, capital letter A, some years ago, was decided by a bunch of people in a room, shall be represented with this pattern of zeros and ones. 0, 1, 0, 0, 0, 0, 0, 1. And now, trained as you are to do a bit of quick binary math, what decimal number is used to represent apparently capital A? So 65, because it's 64 plus 1 plus 1 times 1 is 65. What is B? Turns out it's 66. What is C? 67. So they kept things simple there on out. Might have been nice if A were 0 or maybe A were 1, but nope, we're stuck with 65 instead. But everything after that is very much predictable. And in fact, for lowercase letters, there's a whole other set of numbers, such as lowercase a happens to be 97, lowercase b happens to be 98, and so forth. But again, this is sort of like CS trivia, but what's important here is that they're indeed contiguous from 65 to 66 to 67 on up. That's something we're going to be able to leverage beyond the letter A alone. What is this system? What is this mapping that you yourself proposed? It's ASCII, the American Standard Code for Information Interchange. And indeed, it was a bunch of Americans years ago who came up with this system. Unfortunately, at the time, they only allocated 7 and eventually 8 bits total for representing letters, both uppercase and lowercase, numbers on the keyboard as well, punctuation symbols as well. And so per our conversation a moment ago, if the Americans in this room, so to speak, only used 8 bits total, how many different characters can we represent with a computer in this story? So only 255, technically 256 if we again start counting from 0. So that's not nearly enough but it is to represent all human languages, but it is enough to represent at least English among some others. So here, for instance, is a chart of the ASCII mapping. And sure enough, if we zoom in on like this column here, 65 is capital A, 66 is capital B, dot, 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 72 is H, 73 is I, and so forth. So there is a standardized mapping for at least all of these English letters. Well, suppose you were to receive an email or a text message or like a Google Doc containing this pattern of zeros and ones. So 0, 1, 0, 0, 1, 0, 0, 0, and so forth and so forth. So 3 bytes worth. 3 sets of 8 bits, that is to say 3 bytes, each of which represents a single letter in ASCII. What message have you received? Well, I'll do the math this time so we don't have to. Suppose what you really received was decimal 72, 73, 33. What message did you just receive? If you recall the previous chart. Hi was in fact correct. Why? Because H is 72, I is 73, and wait a minute, 33. So here's H, here's I. 33, if we highlight it instead, happens to be an exclamation point. So like that is literally what is going on underneath the hood, so to speak, when you get a text message today that literally says in all caps and an exclamation point, hi. Your phone has received at least 3 bytes, each of which represents a letter of the alphabet. Your computer is quickly doing the mental math to figure out exactly what numbers those are, and then looking up in the so-called ASCII chart in its memories, in some sense, what letter should you actually see on the screen there. And so if you were to then display that message, you would see it indeed in English as opposed to those numeric equivalents. How else might we use this then? Well, here again is that chart. And maybe just to vary things, maybe take a little pressure off of me here, why don't we try spelling something else? This time a different 3-letter word, but maybe 8 volunteers. Could we get a byte's worth of volunteers? And I can sweeten the deal with some stress balls in exchange. You just have to be comfortable coming up on stage and being on the internet. So yes, 1, 2, how about 3, 4, how about 5, 6, 7, and how about 8? Come on up. A round of applause for our volunteers. Yep, come on. All right, so what I'm going to have each of you do is represent a bit in a particular order. So if you want to just in any order, line yourselves up here facing the audience. Come on over. All right, and we will have you represent, well, we got to see who ends up where. Scooch this way a little bit. This way, this way. All right, so you shall be the 1's place, and just hold that in front of you. 2's place, 4's place, 8's place, 16, 32, 64, and 128. And just compress yourselves a little bit if you could. So each of these folks represents a bit in a particular place. And let's say this. If you're just standing there sort of uncomfortably without any hand raised, we'll assume that you're representing a 0, quite simply. If your hand goes up, though, the audience should assume that you're representing a 1. And therefore, what we'll do is spell out a 3-letter word. And on each round of this, you'll either stay like this or you'll raise your hand. But first, let's actually meet some of our volunteers here, starting with position number 1, if you'd like to say your name, perhaps where you're from and or studying.
Hi, my name is Brooke. I'm from Indiana, and I'm studying biology and computer science.
Nice. Welcome.
Hi, I'm Becca. I'm from Maryland, DC area, and I'm studying electrical engineering.
Welcome.
I'm Addison. I'm from Maryland. I'm studying engineering.
Hi, I'm Sharon. I'm from Rwanda, and I'm studying CS and math.
Welcome.
Hi, I'm Grace. I'm from Alabama, and I'm studying electrical engineering.
Welcome.
Hi, I'm Angelina. I'm from Maryland, and also I stay in Matthews.
Nice. Matthews. Nice.
And I'm studying applied math and econ, as well as environmental science and public policy.
Welcome.
I'm Owen Bells, and I'm from rural Virginia, and I'm studying CS.
Nice. Welcome. And
my name is Max. I'm from London. I'm also staying in Matthews, and I'm studying computer science and neuroscience.
Welcome aboard as well. If you're wondering too why I was wearing these glasses at the start, so very common on the internet nowadays is these POV videos. So it turns out these Ray-Bans actually record video footage, and we have a couple of them, and we thought we'd offer them to a couple of volunteers if anyone wants to record their point of view for everyone here. And Vlad here is going to help make sure they're recording. Second volunteer? Yes, number 2. All right. So as Vlad gets those set, on the backs of your pieces of paper, you have instructions for the following 3 rounds. Each round represents a letter. The audience participation part of this is to actually do the mental math to figure out what number these volunteers are representing. So go ahead and execute round 1, either keeping your hand down or raising it appropriately. OK. What number are our volunteers here representing? 66, because we have a 64 plus a 2. That then maps to what ASCII letter? B was the first letter. OK, hands down. Round 2, go. A little harder. What's now being represented? I'm starting to hear it. 79 is in fact correct. 79 because we have a 64 and an 8 and a 4 and a 2 and a 1. So if it's a 79, we have the ASCII letter O. OK, so we've got B, O, and then lastly, third round, go. We have 0, 1, 0, 1, 0, 1, 1, 1. What number is this? 87, which spells the letter W, which spells the word, not bow. Take a bow if you could. All right, a round of applause for our volunteers here. And come on off this way and help yourself to a CS50 stress ball. Thank you to our volunteers. So this is only to say we've now agreed on how we can represent numbers from 0 on up. We've agreed on how we can represent letters, but at least letters using ASCII. And in fact, these are more than just decoration. In fact, as a little bit of trivia by lecture's end, if you want to come up for your very own CS50 stress ball, turns out there's 64 light bulbs at the foot of the stage here. If you break them down into 8-byte or 8-bit or single byte chunks, there's an 8-letter word that happens to be spelled out today using this here ASCII chart. So today's mystery is, what exactly is that there word? But of course, if you have only 8 bits, you can only represent 256 characters, which sounds like plenty for English. And indeed it is. 0 through 9, A through B, capital and uppercase and lowercase, as well as punctuation. But there's so many other human languages in the world that have other characters. For instance, we have not just the English alphabet we might see here on a US English keyboard. We have accented characters. We have various Asian languages have even many more glyphs. We need more than 256 possible characters. And so nowadays, computers do not just use 7 or even 8 bits. They might use 8 bits for some letters, like all of the English letters. They might use 16 bits for certain other languages, maybe even 24 or 32 bits. And fun fact, if you have 32 bits, and we have more than that on the stage, if you've got 32 bits, you can actually represent as many as 4 billion possible characters, which is quite a bit. No pun intended. So what else can we represent? Well, the goal of this system, not just ASCII, but something known as Unicode, which is a newer standard, is to be backwards compatible with ASCII. So humans left all of those other numbers alone, 65, 66, 67, and so forth. But they added to it a superset of representations that maybe are 16, 24, or 32 bits. The goal being to be able digitally to represent all human languages, past, present, and future, and even through pictograms, things like smiley faces and the like, even people, places, things, and emotions that transcend human language. And in fact, odds are within the past few minutes or hours, most of you have used one or more of these here emoji, these pictograms, which it turns out are just characters on a keyboard. You might have to hit a special button to pull up that form of the keyboard, but these are just here characters. And so these emoji have exploded in popularity for a number of reasons, one of which is, my God, what are we going to do with 4 billion possible patterns of zeros and ones? We can start to kind of have some fun with it and represent things beyond English and human languages alone. Now, as an aside, when it comes to Unicode, it turns out Unicode years ago standardized this pattern of 32 zeros and ones to represent just one of those emoji. So emoji tend to use even more bits here. Anyone know what decimal number this is? This is not a fun mathematical exercise. The spoiler is 4,036,991,106 is the decimal number that actually represents, as of present, the most popular emoji in the world. Does anyone want to hazard a guess what emoji this here number represents? Hearts? No, but it's actually this so-called face with tears of joy. So perhaps think about the frequency with which you send that one. And even though it's obviously a picture on the screen, sure, it actually is more like a font, because underneath the hood, it's indeed just a pattern of zeros and ones or a decimal number that the computer is storing. But the computer, be it Mac OS or Windows or iOS or Android, know to display that pattern as this here picture. But the pictures might look different depending on the hardware. Why? Because there's companies like Google and Microsoft and Meta and others that have their own artists on staff as employees, and those artists interpret the descriptions like face with tears of joy differently. So those of you with an Android phone actually see face with tears of joy looking a little something like this. And if you have Telegram, for instance, installed on your phone, it's even more animated than that. It's this here emoji using the same pattern of zeros and ones. So different artists render these here emoji in different ways, but all they are here are patterns. Now, for all of the other answers, save one that was shouted out a moment ago, this is a sort of cloud diagram of the most popular emoji as of a couple of years ago per Unicode, whereby the size of the emoji indicates its relative popularity. So heart, I did here over here, is indeed one of the most popular ones as well. Question? A really good question. Why do certain emoji not show up on one device or another? It depends on how recent the software is. Pretty much every year, the humans behind the Unicode consortium release new emoji, which is to say they decide that this other pattern will represent this new emoji. This other pattern will represent this new emoji. And unless you update your phone, your laptop, your desktop to the very latest software, and the manufacturer of that device or software also updates by hiring an artist to draw those pictures in their own font, in their own style, you're going to see usually just like an empty black square, or maybe just like a black and white heart instead of something more colorful, really just placeholders. Because it's as though you don't have the right font installed, or really you have an older version of that same font installed. But it's become sort of an annual tradition that new and more emoji are released every year, which is among the reasons why these updates contain more and more. Yeah? That is an amazing segue. How do you represent color in bytes? Well, you use RGB, which happens to be, by coincidence, the next slide. So let's again recap. We know how to represent letters. We know how to represent numbers. We can even represent emoji. But those emoji, technically, on the screen are, of course, composed of colors, like a whole bunch of yellow for that their smiley face. How do computers, then, using only zeros and ones, represent colors? Well, by convention, they typically use a system that, by an acronym, is called RGB, red, green, blue. And this is to say that a computer, to represent a single dot on the screen, maybe this one, this one, this one, will allocate some number of bits or some number of bytes to represent the color of just that there dot, otherwise known as a pixel. You can actually see pixels on your phone or even on your TV or monitor. If you go really close, especially if it's an older monitor, you can see the tiny little squares. Each of those has some number of bits telling the device what color to use. In particular, these devices typically use 3 numbers in total, 3 bytes. So that is to say 24 bits per pixel. And they do this. If you were to represent a single dot on the screen using these 3 numbers, just by intent here, this is 72, 73, 33, which in the context of a text message, an email, a Google Doc,